Hey everyone, so today we're going to continue on 12.3. So I have another example to show you. So this one is about another thing, another favorite of you guys, which would be when you have a mass with a spring, and the spring would exert forces on the mass as it moves around. So what happens when you have multiple masses with multiple spring involved, and therefore would form some kind of system of differential equation. So this is often referred to as a mass spring system. So this is an example given on page 597. So definitely go back to the book and refer to it. So here's the picture that they give from the textbook. So imagine you have two different masses. I'm going to call it mass M1. Let's say it's on some kind of wheel so that it can move freely. And they have a mass number 2, which I'm going to call M2, which also on some kind of wheel so they can move kind of frictionlessly. But even though it's frictionless, it's frictionless, so that way there's no resistance. Okay. Because what I don't want is to add on to our system of differential equation with some kind of resistance which is dependent on the velocity. So assume that these two things can move around left and right with no resistance. Therefore, the only force being acted on them would be what's connecting these two masses together, which would be spring number 1, and then spring number 2, and that's spring number 3. So each of these springs has a different stiffness, which is given by constant K1, constant K2, and constant K3. So in this entire system, this picture kind of shows two weight, which is the M1 and M2 of mass M1 and M2 separated, by springs from each other and from the wall on either side. And each of the spring has a stiffness that's given by the constant K1, K2, and K3, which basically just a proportional force given by the spring. So here we're going to say that the, let's say the stiffness of the springs are basically K1, K2, and K3. Okay, and the idea is that each of these has a equilibrium position, which I'm going to define them to be like right here. So I'm going to say this is the equilibrium position for mass 1. And let's say somewhere over here, let's say is the equilibrium position for mass 2, equilibrium position. So therefore, if they are at an equilibrium position, none of the spring actually exert any force on the system because they are at the equilibrium position. But if either of these two masses move out of the equilibrium position, now the spring would now exert some kind of force to kind of restore it back into the equilibrium position. And so the way it works is to define the displacement. So I'm going to go and call X, or maybe I should say this way, the restoring force and we're going to define them to be proportioned to the displacement from the equilibrium position. So as soon as the mass moves out of its equilibrium position, then the spring would exert forces that would try to push it back toward the equilibrium position. And once again, we're assuming that these two masses can move freely. There's no frictions or resistant forces at all. The only thing that's act upon this are basically the spring exerting a force that restore it back into equilibrium position. We're going to go ahead and call X being the displacement. Let X of t be the displacement of mass number 1, and let Y of t be the displacement of M2. And for both of these displacement, we're going to define it moving to the right is positive. And moving to the left is a negative displacement. And because of the way that it works, that means moving to the right is also considered a positive direction for forces as well as for velocity. And moving to the left is a negative direction, which would be negative velocity or negative force. So now comes the question, how do I describe the movement of these two things? So the way to describe this movement of these two things is to work out the forces involved in each of these masses. Okay? So let's try to figure it out. Let's look at M1. So for M1, how would this thing be affected? What would cause it to move? And by what amount? What happened to this system that would generate some kind of force that would act on M1? Well, let's try to figure out. So first of all, we know that the force, the net resulting force of any mass is basically, according to Newton's law of motion, the mass times the acceleration, which the acceleration for mass number 1 would be how its displacement get accelerated. That would be d squared x over dt squared. And that would be the result of 3 different forces that can act onto this mass. Yes, there are 3, even though there are only 2 springs attached to M1. First, if M1 is out of position, out of its equilibrium position, then the first spring K1 would exert a force that would go in the opposite direction of that displacement to pull it back. Meaning, if M1 moved to the right, K1 would exert a force pulling it back to the left, because it will pull it back toward the equilibrium position. So therefore, the first force I noticed would be negative K1 times X. 2, if M1 move out position, K2 would also exert a force that would kind of move it back. And that would be also moving in the opposite direction of the displacement, meaning if M1 moved to the right, K2 would push it to the left to get it back into the equilibrium position. finally, if mass number 2 move out of the equilibrium position, it would drag along K2 with it and therefore have an impact on M1. And this one is a little tricky because if M2 moved to the right, then the spring would actually drag M1 also to the right and therefore exert a force in the same direction as the way M2 is moved. So therefore this would be plus K2y. So that describes the force acting on mass number 1. Now let's look at mass number 2. So mass number 2, the way the net force on this mass number 2 would actually be m2 d squared y over dt squared, because that would talk about the displacement for mass number 2, which is given by the y function. And so how many forces are acting on this thing? So first of all, notice that if m1 get moved, it would drag along m2 with it because the connection K2. So therefore, notice that if m1 moved to the right, it would push m2 to the right also. So therefore, they actually go in the same direction. So therefore, would be K2x, that amount of force being applied. 2, if m2 itself move out of its position, K2 would have a force that kind of pulled it back toward the equilibrium position. Therefore, would be negative K2y. And if we move, K3 also would exert a force that would kind of push it back to where the equilibrium position is. And so if M2 moved to the right, K3 would push to the left. Therefore, would give us a negative K3y. So notice the positive and negative or plus or minus in the force here are basically defined based on whether it's going against the displacement or going to with the displacement. If it's with the displacement is plus, but if it's against the displacement is minus. So that gives us a system of differential equation. Now all I have to do is kind of put it into the right form. So to do that, what I'm going to do is I'm going to take the first equation, divide by m1, and which is safe to do because m1 can never be 0, because if it's 0, there's no mass. Kind of like in the matrix, there's no spoons. And I'm going to collect some of these together. I'm going to collect the 2x term together. So therefore, I will have this d squared x over dt squared is actually equal to a negative k1 plus k2 over m x plus k2 over m1, I'm sorry, m1, k2 over m1 y. And d squared y over dt squared would equal to same thing over here, but I'm going to have k2 over m2x. I'm going to factor a negative also, minus k2 plus k3 over m2 of y. So that becomes my system of equation, which obviously based on m1, m2, k1, k2, and k3 to determine the actual equation. But those are definitely constant. So for simplicity reason, how about we choose to do the following? We're going to let m1 equal to m2, which equal to 1. And we also go to let k1 equal to k2 equal to k3. They all equal to 1 also. So therefore, basically meaning that both mass 1 and mass 2 are both 1 pound, kilogram, or whatever unit we use. And then the constant for the spring, they're all exactly identical spring, which they all have one stiffness of 1, whatever unit it is. So if that's the case, then now I can define my system of equation to turn into this. D squared x over dt squared would equal to negative 2x plus y. And d squared y over dt squared would actually equal to x minus 2y. And so now it become a lot more manageable, so we can actually solve this system. So let's go and try to do this. So first I notice is that I'm going to move the 2x over. So I'm going to have d squared x over dt squared plus 2x minus y equal to 0. And the bottom one, I'm going to have negative x plus d squared y over dt squared plus 2y equal to 0. So the top one transform into d squared plus 2 of x minus y equal to 0. And the bottom one transform into negative x plus d squared plus 2y equal to 0. So now I have my equation, a system of equation in differential operator form. So I can now use this to solve my system. So what I'm going to do is I'm going to go ahead and multiply the second equation by d squared plus 2. So therefore, my top equation will be d squared plus 2 of x minus y equal to 0. My bottom one become minus d squared plus 2 of x plus d squared plus 2 times d squared plus 2 of y equal to 0. I'm going to add these two things together. The x would cancel out, and therefore combine into this equation, negative y plus d squared plus 2 d squared plus 2 of y equal to 0. So if I multiply this out, that becomes d to the 4th plus 4d squared plus 4 minus 1 become plus 3 of y equal to 0. And that is actually factorable. It's factored into d squared plus 1 d squared plus 3 of y equal to 0, which is nice because it's a homogeneous equation. So I actually don't have to worry about the particular solution, but simply just have to write out the homogeneous solution, which is easy because of the characteristic root. So I'm looking at this correctly. It tells me that the characteristic roots are r equal to plus or minus I, and r equal to plus or minus I radical 3. So therefore, seem to me that my solution for y of t would equal to c1 cosine t plus c2 sine t plus c3 cosine radical 3t plus c4 sine radical 3t. So seem to me that is my answer for y. So that's pretty good. So now just to figure out what x is. So once again, to figure out what x is, I'm going to pick an equation that doesn't require me to solve for differential equation for x, which I'm looking at those two equations. I'm thinking this second equation right here will be what I'm using. So I have d squared y over dt squared is equal to x minus 2y. So nothing to it but go and give it a try. So I do need the second derivative. So that's a little tricky to do. So actually what I'm going to do is this. There you go. I'm actually going to write out my second derivative first. So that will be negative c1 sine t plus c2 cosine t plus radical 3, actually negative radical 3 c3 sine radical 3t plus radical 3 c4 cosine radical 3t. So all the cosine turn into negative sine, and all the sine turn to cosine. And now I'm going to do my double second derivative. So my second derivative actually equal to negative c1 cosine t plus c2 or negative c2 sine t minus, so this one is tricky because I'm going to have to multiply by another radical 3, so it becomes 3 c3 sine radical 3t, or actually cosine, I'm sorry. okay, minus 3c4 sine radical 3t. So now all of them are actually minus. So that actually is okay. So what I'm going to do is now I'm ready to write out my equation. So this basically tells me that negative c1 cosine t minus c2 sine t minus 3c3 cosine radical 3t minus 3c4 sine radical 3t is equal to x minus 2 times y. So therefore become minus 2c1 cosine t minus 2c2 sine t minus 2c3 cosine cube root of t minus 2c4 sine radical 3t. So I know it looked like massive, but technically speaking, there are only 4 terms involved. Cosine t, sine t, cosine radical 3t, and sine radical 3t with their c1, c2, c3, c4 in front. So what I'm going to do is simply move everything over. If I do that, I will have x of t equal to, so for cosine, c1 cosine t, look like I have negative 1 on one side, negative 2 on the other side. When I move over, it becomes positive. So therefore becomes c1 cosine t. Same thing with c2 sine t. I should have one positive left. But for the last two, notice I have negative 3 on both on the left-hand side. When I move the negative 2 on the right-hand side, it still have negative left. So become negative c3 cosine cube root of t minus c4 sine cube root of t. So seems to me that is my solution for x. So now I can put both of these together and write out my answer. Okay, so my answer should be the following. If I write them as x of t, y of t, then that would equal to c1 cosine t multiplied by 1 plus c2 sine of t multiplied by 1, and then look like x are both negative on this case, so therefore plus c3 cosine radical 3t times negative 1 plus c4 sine radical 3t multiplied by negative 1 also. So that come out to be our solution. Now, something very interesting here that I want to point out. Notice that both for function x and y, they both involve sine and cosine. And it's not a surprise that they have worked out this way because in this whole system, it will actually oscillate. If something happened to either M1 or M2, they will both be moving back and forth, back and forth, back and forth, and oscillate. And they actually would not stop oscillating because there's no friction involved. All right. I think that's it for this video. I'll talk to you guys in the next video. Okay, bye-bye.